mass is hung from a spring, and the spring stretches by 12.7 centimeters before it comes to equilibrium. We then take the mass, pull it down by 5 centimeters, and we allow the whole thing to oscillate. And then we want to figure out some things about the motion. So before we get started on this problem, let's just do a quick sketch of what happens. So first we have a spring by itself. Then we hang our 350 gram mass off of it. So M equals 350 grams. When we do that, the spring stretched by 12.7 centimeters. And then what we do is we take that mass, we pull it down 5 centimeters, so we pull it down here, and then it oscillates back and forth about this equilibrium. So this is the new equilibrium. So there's what's happening in the picture. So it's bouncing up and down there. So part A, find the spring constant of the spring. We want to sort out the spring constant. Let's ask what we know, and let's think about the case where it's at equilibrium. So the mass is hung, it stretches down by 12.7 centimeters. And before we pull it down and let it oscillate, so let's draw a free body diagram at this point. We have the spring force pulls up on it, so the force of the spring is equal to K times X. We have the force due to gravity, the weight pulls down on it, that equals mg. Before we pull it down by 5 centimeters and let it oscillate, it's at equilibrium. So if we write Newton's second law, the sum of the forces equals mass times acceleration. We know that it's not oscillating at all, so our acceleration is 0, and the sum of our forces are our two forces. The spring constant, it points up, so it's positive. Take away our weight, because that points down, it's negative. So kx minus mg is mass times acceleration, which is 0, gives us 0. Solve this expression for k, we get mg divided by x, put our numbers in there, 0.350 kilograms times 9.81 meters per second squared, divided by x, the distance stretched from equilibrium, 0.127 meters. Put that through the calculator and we get a value of k equal to 27.0 newtons per meter. Okay, and we notice that k is always going to be a positive value. Next, we're asked to find the angular frequency of the motion. Sometimes that's called the angular velocity. So B is asking, what is omega? Two ways to find omega. Omega is 2 pi over t. That's our definition of angular frequency, but we don't know t. Let's ask if there's another way to find omega. It's also root k over m. Okay, so we can use either of those expressions. So let's use omega equals root k over m. We know k is 27 newtons per meter. We know that the mass on the spring is 350 grams, 0.350 kilograms. Put that through the calculator and we get an angular frequency of 8.78 radians per second. Might also just write seconds to the -1, doesn't matter. Okay, the next part asks for the phase constant of the motion. So part C, phase constant. So phi naught equals, that's what we're trying to find. So phi naught is the phase constant in the equation of motion. X of t equals a times cosine omega t plus phi naught. To find our phase constant, normally we put in some numbers that we know and we solve for our phase constant. So we know that at t equals 0, the mass is pulled down by 5 centimeters. So x is equal to minus 5 centimeters. We know that if we pull the mass down 5 centimeters, it's going to oscillate up and down between -5 and +5 relative to the equilibrium. So our amplitude is equal to 5 centimeters. Okay, now we have everything we need. T is 0, omega is 8.78, amplitude is 5 centimeters, position is -5. Let's put those numbers in. Won't actually write out omega because I know we're doing omega times 0. That's just going to give us 0. So minus 5 centimeters equals 5 centimeters times cosine of phi naught. So phi naught is the inverse cosine of minus 5 centimeters divided by 5 centimeters. Okay, so you got to bring your 5 centimeters over to this side, then you take the inverse cosine of both sides. So we've got the inverse cosine of -1. The inverse cosine of -1 is what angle do we take the cosine of to give us -1? So the answer to that is pi. So cosine of pi is -1. It's not the only answer. It could also be minus pi. So let's write down both answers because cosine of negative pi is also -1. And in this case, pi and minus pi, they're actually the same answer, right? If you think about your unit circle, pi is this angle, minus pi is this angle. Those are exactly the same. So if we're going to pick our phi naught, we can pick either one. They're both right. Okay, so phi naught is either pi or minus pi. And then part D, write the equation of motion. It means write down our equation for x, but put in all of the numbers that we know. So let's do that part next. So part D, x of t equals a cosine omega t plus phi naught. Let's stick in our numbers. So x of t equals 5 centimeters. You can put that in meters if you like, or leave it in centimeters, times cosine of omega, which is 8.78 radians per second, times t, plus our phase constant pi or minus pi. I'm just going to pick pi. Doesn't matter which one I pick, so either is okay. So there's our equation of motion. In the next video, we'll do find the 2 times when x is equal to 2 centimeters.